Welcome to the deep dive. It's late, the servers are humming, and we are incredibly glad you're here.
Yeah, thanks for joining us.
If you're listening to this, you are likely a software engineer. You know how to build systems, you know how to optimize code, and right now you're probably looking at this massive, sweeping wave of artificial intelligence. And
Trying to make sense of what is actually happening under the hood.
exactly, you want to look past the magic and see the metal.
And that is the exact mindset we need for this material.
Yeah.
Because the magic of AI, especially when we talk about large language models generating text, is essentially an illusion. It's an illusion sustained by some absolutely phenomenal systems engineering.
Yeah, and our entire focus for today's deep dive is on one specific piece of that engineering, the KV cache. We are pulling our insights from a stack of notes from the LLM Mastery podcast, specifically looking at an analysis of why LLMs generate text so much faster than their underlying math suggests they should. Our mission today is to unpack this deceptively simple optimization. We are going to see why serving an AI model to millions of users is, it's fundamentally a classic computer science challenge. It's not just a machine learning one.
Yeah, to appreciate the solution, we first really have to understand the nightmare scenario of operating without it.
Which sounds crazy until you look at the analogy in the notes. I love this one. Imagine an accountant doing your taxes. You hand her a receipt, she records it. You hand her another, she records that too.
Makes sense so far.
Right, but now imagine that every single time you hand her a new receipt, she throws away all her previous notes. She starts completely from scratch.
Oh, wow.
Yeah, she re-examines receipt number 1, then number 2, retotaling and re-categorizing everything all over again just to process the newest receipt.
I mean, it's an absurd way to work. By the time you hand her receipt number 500, it takes her 500 times longer to process than the very first one.
Yeah.
By receipt 10,000, you're both dead of old age.
Exactly. No sane professional works that way. She would keep a running ledger and accumulated work product from all the previous receipts, and she would only process the new information.
Right.
In the world of large language models, that running ledger is the KV cache.
And that ledger is strictly necessary because of how these models actually output data. Large language models are autoregressive. They generate text exactly one token at a time, a token being a word or, a piece of a word.
Okay, let's unpack this. The crunch mathematical problem here. I was looking at the math in the notes, and if I'm reading this right, for a 1,000 token sequence, which is maybe a couple paragraphs, the naive approach takes 500,000 steps of work. Is that actually how the math scales?
It is. The underlying architecture forces that behavior. To produce token number n, the model has to perform a massive forward pass where that new token attends to all the previous n-1 tokens.
Ah, the famous self-attention mechanism.
Right. Every token's mathematical representation is computed by comparing it against every single token that came before it.
So to generate token 1, you do one forward pass. For token 2, you attend to 1 and 2. For token 3, you attend to 1, 2, and 3.
Which means the total amount of work scales quadratically. The formula is n times n plus 1 divided by 2. So your reading of the notes is spot on.
Wow.
Yeah. 1,000 tokens requires 500,000 attention steps. If you push that to 10,000 tokens, it jumps to 50 million steps.
That's insane.
If we actually ran models this way, quadratic growth would make generating even a simple paragraph painfully unusably slow. I mean, the compute overhead would melt our servers.
But there's a saving grace here, and it all comes down to determinism. When generating token n, the core data for tokens 1 through n-1 hasn't changed at all.
Exactly. It's pure determinism at play. The attention mechanism calculates 3 specific vectors for every token: a query, a key, and a value. But the keys and values of all the previous tokens are deterministic functions of their position and the model's static weights. Generating token 50 doesn't retroactively change the key and value of token 5. They're fixed. Only the completely new token has a new query, key, and value.
The notes use this omakase sushi chef analogy to explain this, and I think it makes the query, key, and value concept so much more tangible.
It really does.
A chef preparing a multi-course omakase meal designs every dish to build on the flavors of the dishes that came before it.
It's a remarkably effective way to visualize self-attention.
Right, but a chef isn't going to literally re-cook and retaste the first 19 dishes just to figure out what flavors to put in dish 20.
No.
That would be the quadratic nightmare all over again. Instead, she operates like a professional. She keeps detailed tasting notes and she keeps small samples from every previous dish she made. When it's time to create dish 20, she just consults her notes and tastes her tiny samples.
Those elements map perfectly to our attention variables. If you're building software, think of it like this. The brand new dish 20 is the query, or Q. It's asking the system, what am I looking for? Which of these past flavors matters to me?
And the tasting notes would be the key, or pay. The previous tokens standing there saying, here is what I contain, here is a summary of my attributes.
Leaving the small samples themselves as the value, or V. It's the actual content of the past token saying, here's my actual information, mix me in if I match your query.
Yeah.
Computationally, keeping those notes and samples on hand is a massive victory.
Because it completely changes the wall clock time per token.
It turns a system that stalls out into one that functions interactively. By only computing the Q, K, and V for the brand new token and pulling the keys and values for all the older tokens from the cache, we eliminate the redundancy.
Instead of multiplying a giant n by n matrix.
Which scales quadratically and completely chokes memory bandwidth.
Right. We just take the single 1 by n vector of our new token and multiply it against the cached matrix.
Exactly.
Yeah.
It turns an O of n squared nightmare step into a simple O of n lookup and multiply. And GPUs absolutely devour 1 by n vector matrix multiplications.
Yeah.
They're built for exactly that kind of highly parallel, streamlined math.
The total work over the whole sequence is still technically O of n squared, right?
Technically, yes. But because we cache the intermediate states, the real-world time it takes to spit out each new word is drastically reduced.
Here's where it gets really interesting, though, because in computer science, there is no free lunch.
Never.
The KV cache gives us incredible speed, but it demands a trade-off. We are trading computation for memory, and the amount of memory we're talking about is staggering.
It is the defining bottleneck of modern AI infrastructure. To understand why, we have to look at the concrete numbers. The notes provide a breakdown for Llama 270B, which is a great baseline for an engineering audience.
I was looking at that math, and it honestly made me do a double take.
It's sobering. Let's walk through it.
Yeah.
A model like Llama 270B has 80 layers. It has 64 attention heads per layer. Each head has a vector dimension of 128.
Still tracking.
We are caching 2 vectors per head, the key and the value, and we are storing these values in 16-bit floating point, or FP16, which means each value takes up 2 bytes of memory.
Okay, so multiplying that out. 80 layers times 64 heads times 128 dimensions times 2 vectors times 2 bytes.
That gives you 2.6 megabytes of memory required to cache the state of a single solitary token.
2.6 megabytes per one word, or even just part of a word.
Now extrapolate that. Let's say a user sends a prompt and gets a response totaling 4,096 tokens, which is a fairly standard context window these days.
Yeah.
2.6 megabytes times 4,096 tokens equals roughly 10.5 gigabytes of memory.
For one user sequence.
Just one. If you are running a service and you want to handle 32 concurrent users, each with a 4K context window, you need 336 gigabytes of GPU memory dedicated entirely to the KV cache.
Which is wild because standard high-end GPUs like the A100 often only have 80 gigabytes of VRAM.
Right.
336 gigabytes is often larger than the neural network model weights themselves.
During inference, the KV cache absolutely dominates the physical memory of the GPU. It grows linearly with sequence length, and it grows linearly with batch size.
I was struggling to visualize why we multiply by 80 layers until I read the 80-story corporate building analogy in the notes.
Oh, that's a surprisingly accurate way to model a transformer. What stood out to you about it?
Well, the idea is that every floor in this building has its own reception desk, tracking who comes and goes. The ground floor desk is just tracking surface-level things, basic word identities, spelling, grammar.
Right, the syntax.
But as you go up, the top floors are tracking incredibly deep, abstract semantic relationships between concepts. Each floor is doing fundamentally different work, so each floor needs its own dedicated ledger, its own cache. The keys and values at layer 12 are totally different from the keys and values at layer 75.
The architecture demands it. A token can only look at itself and the tokens before it, so this cache across all 80 floors is constantly growing. Token 1 has a cache of size 1, token 1000 has a cache of size 1000.
Yeah.
This is actually why, if you've ever generated a really, really long response from the AI, you might notice the generation speed start to noticeably slow down toward the end. Every new token has an increasingly massive cache it needs to attend to.
Which perfectly explains the daily user experience. It's that exact moment of panic where you're staring at your IDE, wondering if your coding assistant just crashed your machine because it's hanging for 2 full
Oh
seconds.
yeah, we've all been there.
And then suddenly 50 lines of perfectly formatted Python aggressively types itself out faster than you can read it.
That subjective experience is the exact manifestation of the underlying architecture. You're experiencing the two distinct phases of text generation, the prefill phase and the decode phase.
The prefill phase is the pause.
Exactly. During prefill, the model receives your entire prompt at once. It has to process all of those tokens in parallel, doing the heavy quadratic math we talked about earlier to understand the context.
So it's crunching the n squared stuff.
Right. It is furiously building the initial KV cache for every layer of the model based on your input. That's why your IDE hangs for a beat.
But once that cache is built, we cross over into the decode phase.
The decode phase is the fast part. Now, the model is generating token by token. It's relying entirely on the KV cache it just built. It's just doing those fast 1 by n vector matrix multiplications. That's the streaming Python code appearing on your screen.
Okay, so if dedicating 336 digs of contiguous memory is our bottleneck, how are system engineers actually getting around this? Because throwing more hardware at it isn't always economically viable.
Not at scale, no.
Yeah.
This is where we rely on classic systems engineering to rescue us. The solutions look less like pure machine learning and a lot more like operating system design.
I love.
Historically, a naive KV cache implementation would just pre-allocate a massive contiguous block of GPU memory for the maximum possible sequence length.
Like a public library deciding that every patron gets their own dedicated floor-to-ceiling bookshelf, even if they only ever check out 2 paperbacks, the amount of wasted empty space is criminal.
Which is why, in 2023, the VLLM project introduced page detention. And for anyone who has studied OS architecture, this is going to sound incredibly familiar. Page detention manages the KV cache exactly the way an operating system manages virtual memory.
It breaks it into pages, completely eliminating the need for contiguous blocks.
Yes, it divides the memory into fixed-size pages, usually 16 tokens per page. These pages are allocated strictly on demand as the sequence actually grows. And crucially, they do not need to be physically next to each other in the GPU's memory.
Wow.
The system just maintains an index card, a block, table mapping the logical tokens to their physical page locations.
By eliminating the fragmentation and the wasted empty shelf space, the notes indicate VLLM boosted serving throughput by 2 to 4 times. That's 2 to 4 times more concurrent users on the exact same silicon, just through smarter memory management.
And page detention opens the door for something even more powerful: prefix catching. Think of this as advanced memoization for your system prompts.
Oh, this is such a clever implementation. If you are building an app on top of an LLM, you usually have a hidden system prompt. It's a set of instructions telling the AI how to behave. You are a helpful coding assistant, only output Python, that sort of thing.
Right.
And often that system prompt is huge. It might be 4,000 tokens long.
And every single user of your app is secretly sending that exact same 4,000 token system prompt every time they ask a question.
Right.
Under the old naive system, the GPU was running the expensive prefill phase on those 4,000 tokens over and over and over again for every single user, duplicating the exact same KV cache.
Prefix caching solves this elegantly. It computes the KV cache for that 4,000 token system prompt exactly once. It stores it in those memory pages. Then, when a new user connects, the system just maps their session to those existing shared memory pages.
It's beautiful.
It only computes the fresh cache for the user-specific 200-token question. You eliminate 95% of the prefill computation instantly. Time to first token drops dramatically.
What's fascinating here is that software tricks aren't enough. The memory wall is so severe that researchers are actually changing the physical architecture of the neural networks themselves just to shrink the cache footprint.
This brings us to MQA and GQA from the notes, multi-query attention and grouped query attention.
When we did the math earlier, we said Alamey2 had 64 attention heads per layer, and each head got its own key and value vector.
Yeah.
That's standard multi-head attention. 64 separate sets of data to cache. Multi-query attention, or MQA, was proposed as a radical diet. It forces all 64 query heads to share just one single set of keys and values.
The analogy from the notes paints a great picture here. Standard attention is every student in a classroom having their own individual textbook. MQA is the entire classroom of 64 students being forced to share one single textbook.
It shrinks the cache by 64 times, which is an incredible reduction, but it can be a bit limiting for the model's complex reasoning capabilities. So the industry largely settled on a compromise. Grouped query attention, or GQA. This is what LMA2 actually implements.
So instead of one textbook for everyone, or 64 individual textbooks, you put the students in groups. Every group of 8 students shares one textbook.
Exactly. You end up with 8 groups of keys and values instead of 64. It provides an 8x reduction in the cache size with almost no measurable loss in the quality of the generated text.
Which is huge.
Going back to our math from earlier, that drops the cache size from 2.6 megabytes per token down to about 330 kilobytes. Over a 4K sequence, that's 1.3 gigabytes instead of 10.5. You can suddenly serve 8 times as many users without buying a single new GPU.
Okay, so we've shrunk the cache architecturally by forcing heads to share data with GQA. But the notes mention engineers are also just compressing the raw data itself.
They are attacking the problem from every possible angle. One of the most effective methods is quantization. We talked about storing the cache in FP16, which is 16-bit precision. Engineers found you can quantize or compress those stored values down to 8-bit integers, or even 4-bit formats.
Doesn't that destroy the model's accuracy, though, if you're throwing away that much precision in the math?
You would really think so, but the model's attention mechanism has a natural smoothing effect. It actually tolerates this lower precision surprisingly well, effectively halving or quartering the memory footprint yet again.
What about just throwing data away entirely? The notes mention an algorithm called H2O, which stands for the heavy hitter oracle.
That's a form of token eviction. As the sequence gets longer, H2O monitors the attention scores to figure out which tokens the model actually cares about and looks back at the most.
Like a ruthless librarian, it keeps those highly referenced heavy hitters on the fast shelf and quietly deletes the tokens that aren't being referenced, freeing up space dynamically.
Exactly that. And then you have approaches like sliding window attention, which models like Mistral use. Instead of caching the entire conversation history, Mistral enforces a strict rule. We're only going to cache the most recent X thousand tokens.
Oh, interesting.
It creates a constant size memory footprint, regardless of how long the chat gets, based on the assumption that local context matters most.
It's all about fitting more useful state into a tightly constrained space.
If we connect this to the bigger picture, this is the fundamental reality of modern AI hardware. Compute is abundant. An NVIDIA H100 GPU can perform over 1,000 trillion operations per second.
A number so big it barely means anything to a human brain.
Right. The processing power is not the bottleneck. The bottleneck is the memory capacity, which is severely constrained, and the memory bandwidth. The compute units are literally starving for data faster than the memory pipes can deliver it.
Which means the software engineers listening to this deep dive are operating in a very familiar space. Working with LLMs at scale isn't just about tweaking neural net architectures or understanding gradient descent. It is about cache hierarchies, virtual memory paging, database buffer pools. These are the classic foundational computer science problems, just resurrected at a massive modern scale.
Getting it right is quite literally the difference between a cool research prototype that works for one person on a local machine and a production system that can serve millions of users economically.
The source notes do tease that there is an even wilder frontier beyond just caching, something called speculative decoding.
Oh, that's a fascinating concept for the future. If the KV cache is about removing redundant math, speculative decoding tries to break the autoregressive one token at a time bottleneck completely.
Break it how?
It uses smaller, faster models to guess the next several tokens in parallel, and then has the big, heavy model verify them all at once.
Oh, wow. Definitely a topic for another day, but it shows how aggressively this engineering space is moving.
This rapid movement raises an important question, though, regarding the future of system design, as context windows continue to explode.
If page attention maps so perfectly to operating system virtual memory, what happens as these context windows scale from thousands of tokens to millions of tokens? Are we going to reach the AI equivalent of a page fault?
It's a very real possibility. Will models experience cache thrashing, where they spend more time moving memories in and out of the GPU than they do actually computing the text?
That is a phenomenal point to consider. Will software engineers have to design entirely new operating systems from the bare metal up, where the GPU's memory manager has to be almost as intelligent as the AI model it's serving? If the AI is trying to hold a million-page book in its head, how the system swaps those pages in and out of active memory might become the most important piece of code in the entire stack.
It's a deeply complex systems challenge, and it's going to be solved by the engineers who understand both the machine learning theory and the bare metal realities of memory management.
Something to mull over the next time you see that little blinking cursor pause in your IDE
Right.
and then start steering text.
Yeah.
There is an entire universe of engineering happening in that 1-second pause. Thank you for joining us on this deep dive. Keep building, keep questioning, and we will catch you on the next one.